Hello there. Welcome to another problem session. We have an interesting problem today. It's whenever you have a dynamic circuit, you probably remember from my previous lectures, the dynamic circuit is when you have a changing magnetic flux through. So we just say when d phi of magnetic flux dt is not zero. So we're talking about this area where the magnetic flux through it is not changing. It's changing. So the derivative of with respect to time is not zero. So this means EMF is induced, and this means the E dot dl is not zero, right? So this is a related concept that's coming from Faraday law. Okay, so when you have a dynamic circuit, just a wire is connected across this terminal and a lead current T. So if you don't have a dynamic circuit, you just say what's the current, where this resistance is R, then if not dynamic, you can just assume, but it is dynamic because as the current was zero and current is non-zero, so the magnetic field created by current will change through this, and so it is a dynamic. But suppose you said not dynamic, then you'll say I equals to V over R. That will be the answer, but that's not the answer here. Okay, so what happens, the current will slowly build up to a final value. It's kind of may look, suppose I ignore the capacitance of the circuit, then the current will slowly build up, ignoring C, a capacitance, it will build up like that, and this will be V over R. It will be final determined by R, but that will be the final current. So it's going to be like build up to that. This we have done in another video. However, if you have a C, then you're not going to get this. Actually, in the lab, you're always going to have all of these facts, and so it might kind of it's building up, but it can be ringing like that, and we should try to find out what this will be like. Okay, it's the actual that you're going to see in the lab. All right, for that you can't ignore C, and so you need to think about this as a circuit which has both all three: resistance, self-inductance, and capacitance. So if you want to think about it, you can kind of write an equivalent circuit. The equivalent circuit will be like this. So this is T equal to 0. So you have L element, you have C element, so an R element. So here this circuit is equivalent of that circuit. This is what's happening in the lab, and this I'm gonna think of it this way, just properties. So these are all resistance property here, because you understand that, right? Of course, I could in this circuit introduce heavy L values, like you can have an inductor, and you can like a solenoid with an iron core or something like that. Then it will dominate the rest of it, so you'll have that value. You can have capacitor inside there. Even if you don't have any of this, it looks like you don't have really those things there, it's still a single wire like that has those properties, and I'm going to assume that those properties are present, and when I write an equivalent circuit, it looks like this. And so this is the way we're going to deal with this and write equation for this, try to solve the equation for this, right? So if you have a sense of how to do it, go ahead and do it. It's going to require calculus, okay? So do it's going to require calculus. So if you don't have a calculus background, you probably can use the final answer we'll get, but without the calculus you won't be able to proceed. Okay, so I'm going to pause it and clean up and say get you started and answer. Okay, so dynamic circuit means you don't have all this Kirchhoff rules, right? You have a Faraday law. That's what you gotta do. So the Faraday law is do this minus E dot dl equals ddt, and this is what I've been calling EMF for me, but this is, some people don't do it that way. B dot n hat dA, and if the current so this is equals if only I, or current I of t, so that's the only place time dependence, not the circuit is rotating or becoming bigger or smaller. Okay, so if that's the only thing, then I can write this as L di dt, and L will be the self-inductance of the circuit. So I don't have to really work out the magnetic field, etc. You just can write directly that. So what is this? When I go through the circuit, I already took care with the right hand side. Okay, now I need to take care of these two guys. Through the resistor, it's just going to be minus I times R. Oh, I'm going to go through this. I got a V naught. This is V naught. This integral through this gives me V naught, and through this gives me minus IR, because I'm going to go, DL is in the same direction. So the DL for this is DL. So that's the DL. That's the DL. DL is in the same direction as the current, and then it's going to get minus IR. I'm going to go through this capacitance. Capacitance capacitor formula is Q equal to CV, right? So I'm going to get this will be just Q versus C. Our Q equals to I dt. So I'm going to get a minus, because this voltage is going to go drop across here. So the minus, so I have to write an integral. Okay, so 1 over so this will be 1, bring it over here, so this is going to be 1 over C. So the voltage will be this integral, so 1 over C integrate up to some time t, 0 to t, and that will be I of t, let's call it t prime, dt prime. So I'm going to have this, and the other side, so on the other side I'm going to have L di dt. So this is just a constant here, so I can actually absorb this constant in here by defining, you can see you can minus R I minus V0. So if you do this this as some kind of new I, let's call it I prime, then V0 over R, I mean, then I prime, then di prime over dt is same as di over dt, because these things are constant. But if I integrate over I, so I of t prime dt, then I'm dt prime, then this is going to be integral over I prime of t prime plus V0 over R dt prime 0 to t. So you can see I can integrate, or I can replace there, and so I can absorb this in a new equation with I prime. But that's not what I'm going to do. I'm going to there's a couple of ways to proceed here. Okay, so you have a V0 equals L di dt plus IR plus 1 over C 0 to t I t prime dt prime. So that's one way to write this, and then if I call this Q of t, then this is V0 L d square Q dt square, right? So Q of t, then this will mean dq dt equals to I. So wherever I see I can replace with d square, and then I have a R dq dt plus 1 over c q. So I can solve for q and then use this to get the current. So how do you solve this? Well, you probably solve this before divide by L. So let's see. So this is like a mass, and Q is like x d square x dt square, and this is like a B dx dt, and this is like omega square, omega 0 square x, and this is the driving force. So this equation must be familiar to you. This equation is simply equation you did driven, damped, driven oscillator. So all the things that you learned over there, you can just completely carry over this way here, right? So you can see the R is like a damping, L is like a mass, but 1 over C is like a frequency squared if X is Q. Okay, I'm going to, let's just copy from here and then find out what my solution should be. All right. Yeah, here I made a little mistake here. This little, because I thought I divided by m's and I made a mistake. So this is just a kx, k, not omega square. This is a mistake here. So just trying to erase, and I found that this is a mistake. Okay, so let me write down the answers I'm gonna get. So I have based on this, based on these guys, you have omega naught square equals to k over m. So that will go into 1 over c. Omega naught square will become 1 over c over L is 1 over LC. So there's a natural frequency in the circuit, and it says it oscillates. The natural frequency and the damping parameter is in such a sense that it's going to oscillate. And then we have a B over M. So we define what is called 2 beta is B over M. So B equals to 2 B over 2M. Beta is, that's the beta will be R over L. So R over 2L. That's what beta will be. And so what we get is omega for just the damped. So omega is square root of omega naught square minus beta square, and omega naught square minus beta square, and that's omega naught greater than beta, and this is the case of oscillating, so-called underdamped oscillator. So if there was nothing on this side, just this equal to 0, so if this fd equal to 0 will means x of t is some amplitude e to the minus beta t times some cosine this omega t plus a constant. So there are two of these constants are this and this. We need to find what their values are, starting from the initial values. Okay, and because fd is 0, fd is not 0, fd is not 0, so we're just gonna call this guy is x when fd is 0. So x, let's say x free, you can call it, okay, and x complementary. And if it is not 0, then the particular solution will be, if this is a constant, so we gotta guess the answer. So this will be x of t has to be some constant, just be equal to whatever f of d is over k. And so in our case, you can just see from here plus x of c. So this is the answer. So this is the answer for us. So in case of writing for q of t is equal to, what is fd is v0, and what's the k? K is 1 over c. Q equals cv. That's really nice, right? And then you have a xc, which is some a has to be some q, so let's call it some q0. I'm going to call it q0, e to the power minus beta t, and cosine and omega t plus some phi. So that's the answer for q. And let me again, these are still not determined. This is not known and this is not known yet, because that has to be fixed given the initial situation. Let me erase and get myself some more space. Okay, remember, recall that this is just a convenient variable. There is no q anywhere, or just there's a current, right? So what I want is I of t is going to be dq dt. So I can do this out over here. So this gives me 0. So I went through all the stuff, but I still got a 0, taking a derivative of this whole thing. Plus, so all of this, I need to have a q0. We'll take a derivative of this minus beta e to the minus beta t, and you have a cosine omega t plus phi. And then I've got a minus, cosine becomes sine, q0 e to the minus beta t, and omega comes out sine omega t plus phi. Okay, this is the current, and we have to kind of find a way to find these guys in our particular situation. So one of the things here is when I at time equal to 0, when I close the circuit, there was no current, it must be 0. So that's one condition. So that's going to fix one of them. So if it fix one of them, what do I get here? I get minus beta q0 e to the power minus beta t. This becomes 1, and this becomes cosine phi, and then this whole thing is minus q0 omega and sine phi equal to 0. So if q0 is 0, then I have no solution whatsoever. So it is we'll say the q0 is not 0. So we can see here that, and beta is not equal to minus omega, so you can say q0 beta cosine phi minus omega sine phi equal to 0. And this is not 0, then we require that this is minus here. This require that this is equal to 0. So tangent phi equals minus beta over omega, right? So this tells me what phi is, right? Okay. Okay, so we got the phi out from one condition, from this condition. What's the other condition? Well, if you assume that this is the equivalent circuit, so what's the charge here at time t equals 0? Charge is also 0. So that's also 0. So we use that q of 0 equal to 0 over here. Then that just gonna give me, and phi is already known, which is this. So let's see, we got a 0 equals to cv0 plus q0, and this becomes 1, and they have a cosine of phi. So tangent phi is that, right? From there, actually I can get what cosine phi is. So 1 over tangent square of phi is sec square of phi, and just gonna have a, so this is square root of that, so this is equal to 1 over cosine phi. So cosine phi will be 1 over square root of 1 plus tangent square of phi, tangent square of phi. So we can just from here you can see 1 over square root of 1 plus beta square over omega square. So this is omega over square root of omega square plus beta square. So I already know that, so we can kind of replace that, omega over square root of omega square plus beta square. So q0 is that. Q0 is simply, in our problem, minus c square root of omega square plus beta square over omega v0. So going back to I of t, you can see that I can use this q in here, and this phi in here, and that's our solution. It's a kind of a little complicated solution. So, but I'm not interested in how complicated it is, but I'm interested in understanding the conceptual things that went in here. Let me say it one a little bit, repeat some of the things that we had simply a wire connected to that, and I couldn't use this as an answer, right? That was not going to be the answer because this is a dynamic circuit. So the dynamic circuit will always have an self-inductance to the circuit, so just isolated that. And because it said it was a ringing, then really I couldn't ignore the capacitance either. And the damping will come from the resistor. So it's kind of a circuit with a like a fixed voltage, but circuit was turned on at time t equal to 0. And so it's going to build up from there, and along the way the current will vary. So the yeah, you can see already that answer can be quite complicated, but if you had a numerical values, so that damping was not critical damping, not over damping, but under damping. And then we could just borrow the solution that we learned in mechanics to solve this problem. I hope you learned a lot. If you learned a lot, please hit the like button so other people can actually get access to this video. If you subscribe to this channel, if you haven't subscribed, I'll appreciate if you subscribe, because it also helps distribute the content a little bit. And if you wanted to learn more about these kinds of approaches to physics, introductory physics, you can go out and study in that website that I maintain. And it's constantly I'm improving that website. There's some things I've added already, and there are more things to come on that website. And that's it. Take care. Bye-bye.